revision of exercise 5A, 5B, 5C, and 9G. I do recognize there's a lot of exercises there, but a lot of the content is very, very similar, which is why we're going through it in this order. Instead of going from exponentials and then logarithms, and then later down the line going to differentiation of exponentials and logarithms, why don't we just do exponentials all together and logarithms all together? So that's why we're doing it in this order. But first we need to apply understanding from the chain rule in this do now question, where we have x to the power of 3 plus 1 or to the power of 30. In this situation, of course, a valid option is to simply expand it out to the power of 30. That is a valid option, but unfortunately, I think you won't be using much of your exam time for the rest of the other questions. So let's use the chain rule so that we save ourselves some time and just simply apply from there. I prefer Leibniz's notation, so we're going to go ahead and use dy dx equals to dy over du times by du over dx. Please remember, this formula and this concept is super relevant, and I always make a bet and say that a question involving chain rule will always come up on the VCAR exam with that question. No pun intended. But most of the time it comes up as a short answer, but it is super relevant and you should definitely know how to do it. So we've got this question here, we know the formula, let's define our equation. So let's say y equals 2 u to the power of 30, where u equals 2 x cubed plus 1. So I've just defined the inside as u, which means I can actually get rid of these brackets and just write u to the power of 30. From there, I know that dy du, or in other words, the equation of y in terms of equation of u differentiated, gives us 30 u to the power of 29, and I know that du dx, as in the equation of u derived in terms of x, gives us 3x squared, and that's it. Now we multiply them together, of course, because the formula is then multiplied together, which gives us dy dx equals to 30 u to the power of 29 multiplied by 3x squared. Sweet, are we done? Why not? Thank you very much, because we define u. If you leave it in that format, it is technically incorrect because we have not actually given the answer. Okay, so we need to substitute it back in. So we get 30 brackets, and we'll write x cubed plus 1 to the power of 29 times by 3x squared. Can I simplify that without making a whole bunch of expansion and whatnot? How do I simplify it, Renuka? Lovely. I can just multiply them, so I get 90x squared, and then brackets x cubed plus 1 all to the power, just that to the power of 29. Okay. That final step, when we're simplifying that, isn't explicitly necessary, but a lot of the time you've provided a question in two parts, where the first part is to derive, second part is to use the differentiation, and most times that simplified version is a little bit more helpful. Sweet. Jumping into some revision content. If I'm going too quickly, please feel free to let me know, but it is expected you guys have a general understanding of the concepts covered here. So with exponential functions, we're revising our understanding of what they look like, both without Euler's number, yes, it's pronounced Euler, very weird word, and just basic numbers in general. So we've got the graph of f of x equals to a to the power of x, where our value of a is positive, which is just this one here. We're super familiar with this. This is what we looked at when it came to, for example, the COVID statistics stack we looked at last year. Of course, if the value of a, so the base number here, is negative, our function goes downward slope. One key point, I should say that, of course, we were familiar that there is a horizontal asymptote, but there is no vertical asymptote. I know it looks like it. It looks like it'd do this, and you'd have an asymptote here, but please note that there is no vertical asymptote there. It is possible for it to go towards infinity for the value of x. Okay. Of course, the maximal domain is going to be all real values of r, or all real values of x, sorry, and the range is going to be all positive values, not including 0, which is why we've got r positive, because you can't have 0. That's where our asymptote is. So r positive is all real numbers that are positive. In the form of this right here, where y equals to a to the power of b, bracket x minus h, bracket plus k at the end, where b is a non-zero number, specifically a positive number. we can say that it's dilated by a factor of 1 over b from the y-axis, followed by the transition, and you guys are familiar with the basic transition there. Do note the dilation and then the translation. Just in case you've forgotten, typically we follow the formula, or the rule I should say, of DRT, to dilation, reflection, and then translation. Okay. Euler's number. Euler's number is a very specific number. It has a place on your calculator, just in case you're not familiar. We've got E equals to the limit as n approaches infinity, where we have 1 plus 1 over n to the power of n. Don't ask me how we came up with this number. Unfortunately, I'm not that smart. But that is Euler's number, and we're going to be referring to that as an irrational number. Just like pi, it doesn't finish, doesn't end, I should say. But as we approach infinity, the value of E is equal to 2.718, and we can leave it there for our interpretation. But no, it does go on forever. Now, the key understanding from the value of E is that E to the power of x derived is just E to the power of x. It's very mind-boggling, but the idea is, if I, for example, let's say this blue line here, that blue line is y equals to E to the power of x. If I was to derive it, is the same value at every point as if I was to sub in x equals to whatever it is. So, for example, x equals to 3, the derivative, or the gradient of E to the power of x at x equals 3 is what I just sub into E to the power of x, or E to the power of 3. Very weird, very confusing, but it is a very distinct property of the Euler number. Exponential equation, this one is pretty much straight up revision. Just remember that if we have a to the power of x equals to a to the power of y, if they've got the same base, and there's no coefficient or anything like that, if they're just the same base, then the powers are implied to be the same. And it is a valid step to go from this line to this line here. We don't have to explain why that is a valid step. But that is assuming that a can be any real positive number excluding 1. Why can't a be 1 in this situation? Why does this rule not hold up if a equals to 1? Well, if we think about it with a specific example, if 1 to the power of x and 1 to the power of y, it doesn't mean that the same thing. It doesn't mean that x equals to y, because x could be 3 and y could be 2. Of course, the numbers are different. X and y will be different, but in this situation, that does work. 1 to the power of 3 is the same as 1 to the power of 2. So this rule only applies when a does not equal to 1. Welcome. Of course, we're going to be using this as revision. So 3 to the power of 2x equals to 27 minus 6 times 3 to the power of x. When you look at this equation, what's the first thing you recognize? Come on, you guys were riveted about exponential equations last year. What's the first thing you recognize when we look at this equation? 3 is a factor in each of them. So Megan, what do I have to do then? What could I do?
Make 27 3 to the power of.
I could, but I know from experience that that's not going to help us as much. Purely because I see this. What can I do with this one right here? Using my index laws, do you agree it's the same as if I do this? Same thing? Yeah? It's still the same thing. I've just taken it out of the brackets. I'm going to go ahead and move this to the right, not change the value at all, just move it to the right. So you end up with negative 6 times by 3 to the power of x plus 27. Riley, any idea what I need to do next? Or what I could do next, rather? We could, but I'm going to focus on the 3x there, yes. Thank you very much. You notice that, let's say I rearrange it and I put everything on one side. Equals 2, I'm going to add, oops, not add equals, sorry. I'm going to add both sides, positive 6 times 3 to the power of x minus 27 equals 0. You'll notice this is just a very complex form of a basic quadratic. If I let a equal to 3 to the power of x, we have a squared plus 6a minus 27 equals 0. All of a sudden seems a lot more solvable, doesn't it? What approach might I use for this one now? Caitlin? Yeah, easy. Let's do cross method. I know that if I do a and a, they multiply to give me a squared. I know negative 27. I can multiply 9 and 3, which looks like it works out really well because I've got a 6 there. So I go 9 and 3. I just need to figure out which one is negative, which is easy. Because when I multiply them out, I get 9 minus 3, which is a 6. Perfect. I'm going to draw my line across, and we end up with a plus 9, a minus 3 equals to 0. Sweet. Are we happy with that? No? We have to solve it, don't we? A equals to negative 9 or 3. Now are we happy with it? Why not? Good, thank you very much. So I'm going to write this over here, just so we have space. Remember, we let a equals to 3 to the power of x. So 3 to the power of x equals to negative 9. 3 to the power of x equals to 3. Now, obviously, the first one, pretty straightforward. X equals to 1. Bottom one. What are we thinking?
It can't be a negative.
Can't be a negative. Why do you say that?
Just can't.
Just can't? Remember, anything to any positive number to the power of a negative number would just be a positive fraction. So, for example, 3 to the power of negative 1 is just 1 over 3. 3 to the power of a positive number, of course, gives us a positive number anyway, so this one does not exist. So I'm just going to write an NA for here, and so the answer is x equals to 1. Very long process, but the point where we have to say that x equals to 1 and 3 to the power of x equals to negative 9 does not yield a result, a defined result, is a process you need to know for a VCAR exam. Okay. Jumping down to here, I do realize I've written all over this, so I try and separate it there. Differentiation of e to the power of x. Once again, reminder that the differentiation of Euler's number to the power of x is just Euler's number to the power of x. It's a very distinct feature there. However, the rest of our differentiation rules apply. So if you have, for example, f of x equals to e to the power of kx, the derivative is just the number multiplied to the front. You can think of it this way. We can derive k times x to give just k, and multiply at the front just like we would for a chain rule or whatever it is. Assuming, of course, k is a real number. Let's put that into practice using chain rule with differentiation of e to the power of x. So with e to the power of x squared, I don't know if you guys can see it up the back, Patiri? Yeah, lovely. E to the power of x squared, we can treat it as we would the chain rule. Now, I'm not going to go through every step in the chain rule because I'm assuming you guys are generally quite familiar with it, but we can define the power as its own function. So, for example, e to the power of u. E to the power of u. Now, we can do the same thing we would before, derive the power, and then bring it to the front, and we'd leave the same. Okay, so e to the power of x squared, of course, if I derive x squared, we end up with just 2x. So I know that f of f dash x equals to 2x times e to the power of x squared. Any questions about that? Remember, the unique property of Euler's number, is that when we derive it by itself, it stays the same. But if it's got other things in it, we have to treat it as if we've got other equations, functions in it, etc. We do the same thing for e to the power of x squared plus 4x. Of course, I'm going to derive the function at the beginning. So I'm going to say, all right, x squared plus 4x, what's the derivative of that? 2x plus 4. Easy. So I'm going to f dash x, equals to 2x plus 4 multiplied by our original equation, e to the power of x squared plus 4x. That's it for revision. I'm going to pause the recording.